In the mid-20th century, the prevailing scientific model for Venus described a wet tropical planet. Because the cloud cover was so dense, astronomers assumed the surface was shielded from the sun, creating a humid swamp potentially capable of supporting life. This assumption was so embedded in the mission planning that early Soviet probes included sensors specifically calibrated to detect water. The reality was the exact opposite. The atmosphere was not a shield. It was a lid that trapped heat, creating a runaway greenhouse effect with surface temperatures of about 475 degrees Celsius. The first few probes didn't just fail. They were physically obliterated by the immense atmospheric pressure before they could transmit a single image from the surface. This failure created a new consensus. Even if a lander survived, photography was useless. The atmosphere was 90 times denser than Earth's. Scientists predicted that little to no sunlight could penetrate that depth, meaning the surface of Venus was locked in perpetual absolute darkness. The Soviet engineers ignored this model. They equipped the Venera 9 lander with a floodlight just in case, but they also programmed the camera to scan immediately upon landing. The footage that returned proved the darkness theory wrong, but it was the later missions, specifically the panoramas from Venera 13, that sent back data no one can fully explain even today. Understanding the full significance of these achievements requires stepping back and examining the enormous technical challenges that the Soviet space program had to overcome. The exploration of Venus represented one of the most ambitious and dangerous undertakings in the history of robotic space exploration. Every aspect of spacecraft design had to be fundamentally rethought and reimagined. The engineers were not simply building a spacecraft to land on another world. They were constructing a machine capable of surviving conditions that seemed almost incomprehensible when measured against human experience or the requirements of terrestrial machinery. The Soviet engineers were working with bad data. 1967, the accepted model suggested this pressure of Venus was roughly 20 times that of Earth. This was high but manageable with reinforced aluminum. The Venera core probe was built to these specifications. It entered the atmosphere and deployed its parachute, expecting a drift down to the surface. It never made it. The probe stopped transmitting at about 27.7 kilometers. It did not burn up. It was physically crushed by the pressure, which far exceeded its structural limits. The atmosphere at that altitude was already surpassing the probe's design capacity, and it was nowhere near the ground. This failure revealed the scale of the problem. The pressure wasn't 20 times that of Earth. It was closer to 90. At the surface, that is the equivalent of being 1 kilometer underwater on Earth. The team had a limited window before the next launch opportunity in 1969. They could not redesign the entire pressure vessel in time, so they tried to bypass the problem through descent speed for Venera 5 and Venera 6. They reduced the size of the parachute. The logic was simple. If the probe fell faster, it would spend less time in the upper atmosphere. Hopefully, it would reach the surface before the heat and pressure destroyed it. The plan failed. Both probes imploded roughly 11 kilometers above the surface. This forced a total redesign for Venera 7. The engineers abandoned the idea of a standard aerospace vehicle. They effectively began building a submarine. The new design featured a forged titanium sphere capable of withstanding 880 atmospheres, double the expected load. They removed almost all scientific instruments to save weight for the armor. The windows were removed. The solar panels were replaced with a heavy internal battery. Venera 7 launched in August 1970. Upon arrival, the parachute reefing cords melted, causing the parachute to fail during the final stage of descent. The probe didn't float down. It fell. It impacted the surface at roughly 17 meters per second. In mission control, the telemetry stream flatlined immediately. The mission was marked as another failure. It was only during a post-mission review of the raw radio tapes that an astronomer noticed a pattern in the static. The probe had not died. It had toppled over on its side, pointing its antenna away from Earth, but it was still whispering. By processing the noise, they recovered 23 minutes of temperature data from the surface. It was the first time a human machine had transmitted data from the surface of another planet. The data confirmed the surface was roughly 475 degrees Celsius. It proved a machine could survive. But it also proved that any camera sent to this world would need to be built like a tank. The survival of Venera 7 marked a fundamental turning point in the program. Before this success, the Soviet space program had been throwing spacecraft at Venus with minimal confidence in success. The engineers had been operating in almost complete darkness, making educated guesses about atmospheric conditions based on incomplete observations from orbit and theoretical models. Each failure provided crucial information that shaped the next attempt. But the program was operating on the knife's edge of budgeted constraints and political will. The international space race was being tuned down by the early 1970s, and there was no guarantee that the Soviet government would continue funding what appeared to be an endless string of failures. The fact that Venera set to survived, even in the most damaged and compromised state, provided the validation that the entire approach was fundamentally sound. Yes, the titanium sphere concept worked. Yes, a machine could endure the pressure. Yes, could be recovered even from a probe that had fundamentally in its primary mission. The survival of Venera 7, that a titanium sphere could resist the crushing pressure of 90 atmospheres. The problem for the next generation of probes was the temperature. The surface of Venus sits at 475 degrees Celsius. This is hot enough to melt lead, zinc, and tin. It is also hot enough to destroy standard silicon electronics instantly. The engineers could not simply insulate the lander. Insulation only slows down heat transfer. Eventually, the heat gets in. They also could not use active cooling systems like fans or radiators. A radiator works by dumping heat into cooler air. On Venus, the air outside is hundreds of degrees hotter than the machinery inside. The solution was to turn the lander into a temporary heat sink. Before the lander separated from the orbiter, the system circulated supercooled fluid through the pressure vessel. This brought the internal temperature of the probe down to -10 degrees Celsius. This gave probe a thermal head start. It essentially began its mission as a block of ice falling into a furnace. To handle the heat generated during the descent, the engineers use phase change material. They packed the interior with lithium nitrate trihydrate. This chemical has a melting point of 30 degrees Celsius. When a substance melts, it absorbs a massive amount of energy without rising in temperature. As the heat from the Venusian atmosphere penetrated the titanium shell, it went into melting the lithium nitrate rather than frying the electronics. This bought the lander roughly 50 to 60 minutes of operational time before the system boiled over and failed. The innovation of using phase change materials represented a sophisticated understanding of thermodynamics applied to an extreme engineering problem. The engineers recognized that they could not fight the heat directly. The Venusian surface was too hot, the temperature differential too great. Instead, they needed to delay the inevitable by pre-cooling the spacecraft and packing it with a substance that would absorb enormous quantities of thermal energy during its phase transition. They could buy time. Those 50 to 60 minutes of operational time represented the window during which all of the spacecraft's critical measurements had to be made. The entire mission had to be compressed into that narrow margin. The cameras had to scan quickly but carefully. The soil analysis equipment had to function reliably. The atmospheric instruments had to take their readings. There was no second chance. There was no ability to restart the system if something went wrong. Every moment counted, because every moment brought the spacecraft closer to thermal failure. The camera itself required a completely different approach from standard photography. A television camera from the 1970s used a cathode ray tube. These tubes were large, fragile, and required glass lenses that would crack under the external pressure. The engineers could not risk putting a large glass window in the side of the pressure vessel. A structural failure there would cause an immediate implosion. Instead of a camera, they built a telephotometer. This is a mechanical scanner rather than a lens-based imaging system. The device remained safely inside the cooled titanium sphere. It looked out through a tiny cylindrical quartz window that was thick enough to withstand the pressure. The mechanism was simple and robust. A small mirror rotated back and forth behind the window. It collected light from a single point on the surface and directed it into a sensor. The sensor measured the brightness of that single dot. Then the mirror moved slightly to measure the next dot. The probe transmitted this data as a stream of numbers. It did not send a video signal. It sent a long string of telemetry that Earthbound computers reconstructed line by line. This method was slow. It took many minutes to build a complete panoramic image. If the probe overheated before the scan was finished, the image would cut off. The engineers were trading speed for durability. They were betting that a slow mechanical eye had a better chance of surviving the conditions than a complex electronic one. The telephotometer represented a brilliant engineering compromise between the need for imaging and the extreme environmental constraints. A conventional camera, with its complex optics, its sensitive electronics, and its precise power management, was simply not viable. The telephotometer took a different approach. By using a rotating mirror and a single sensor, it reduced the system to its most basic mechanical components. There were no complicated circuits that could fail. There were no delicate lenses that could shatter. There was simply a mirror that moved and a sensor that measured light. The data was transmitted as raw numbers, which meant that the processing and reconstruction happened on Earth, where computers had all the power and cooling they needed. This fundamental rethinking of how to accomplish imaging in an extreme environment demonstrated the creative problem-solving that characterized the Soviet space program at its best. On October 22, 1975, Venera navigated the descent and transmitted data for approximately 50 minutes. It landed on a steep slope of roughly 20 degrees. The engineers had prepared for the worst-case scenario regarding visibility. They assumed the thick clouds would block all sunlight, plunging the surface into a deep twilight or total darkness. To counter this, the lander carried powerful halogen floodlights to illuminate the ground in front of the camera. When the lens cover popped off, the sensors detected immediate illumination. The floodlights were unnecessary. The surface of Venus was not dark. The ambient light levels were comparable to a cloudy summer day in Moscow. The thick atmosphere scattered the sunlight evenly, creating a soft, diffuse glow that eliminated harsh contrasts, but provided plenty of light for the telephotometer. The camera began its scan. It took 30 minutes to build the full panorama. As the data arrived on Earth, the scientists saw something that contradicted years of theory. They expected to see a sandy desert or a landscape worn smooth by erosion. The atmosphere was dense, so they assumed strong winds would scour the rocks down to pebbles. The image from Venera 9 showed the opposite. The ground was covered in sharp angular rocks. The edges were jagged and broken. This implied that the surface was geologically young. It also proved that the wind speed at the surface was negligible. The rocks had not been eroded by wind or sand. The atmosphere was calm. The image also revealed the clarity of the air. There was no fog or dust near the ground. The horizon was clearly visible in the corners of the panoramic frame. The probe was sitting on a pile of tectonic debris, likely a result of the landing itself or a recent geological shift. The discovery of sunlight on Venus's surface was revolutionary. For years, scientists had operated under the assumption that Venus's atmosphere was so thick and so laden with clouds that the surface existed in complete darkness. This assumption had profound implications for how the planet was understood. A dark, lifeless world seemed more likely than one bathed in light. The fact that sunlight could penetrate the clouds, even though it was scattered and diffuse, suggested that the planet's surface was not a completely alien hellscape. The light was warm and golden, filtered through the carbon dioxide atmosphere. In some ways, it was more familiar than expected. However, the light came at a cost. That same atmosphere that scattered the sunlight thinly also trapped heat with devastating efficiency. The light that reached the surface was not helping to make Venus habitable. It was contributing to the infernal temperatures that made the planet the most hostile place in the inner solar system. 3 days later, Venera 10 landed over 2,000 kilometers away and operated it for 65 minutes. It touched down on a much older holder. Its images showed flat slabs of rock resembling dried magma flows. The difference between the two landing sites proved that Venus was not a uniform wasteland. It had distinct geological regions. It had mountains, slopes, plains. The primary discovery, however, remained the light. The fact that the sun could penetrate 90 atmospheres of carbon dioxide showed that significant diffused sunlight reached the surface, contradicting earlier predictions of total darkness. These two black and white images were the first direct look at the surface of another planet, but they were limited by their lack of color. The scientists could see the shapes, but they could not see the true nature of the chemical world they had touched. The geological implications of these images were staggering. Scientists could now begin to construct a more accurate picture of Venus's surface. The presence of angular rocks at one site and smooth lava flows at another suggested that Venus was geologically diverse. The planet was not a static, unchanging world. It had been shaped by geological processes similar to those on Earth. There were volcanoes and lava flows. There were tectonic processes that moved and fractured the crust. Venus was, in many ways, Earth's sister planet in terms of basic geological composition and processes. However, the environmental conditions were so different that the analogy broke down quickly. On Earth, the rocks were weathered by water and wind. On Venus, the rocks were baked by heat and subjected to crushing pressure, but little erosion occurred. The surface was geologically young because the harsh conditions did not allow for the slow weathering that would smooth rocks over millions of years on Earth. In March 1982, the Soviet Union launched the Venera 13 and Venera 14 missions. These probes represented the apex of the program. They were heavier, smarter, had more instruments than their predecessors. The primary goal was no longer just to prove the surface existed. The goal was to characterize it chemically and visually. To do this, they engineered the telephotometers to capture color. Venera 13 landed on March 1, 1982, and survived for a record 27 minutes. It began its scanning sequence immediately. The camera did not take a single color photograph. Instead, it took multiple scans using red, green, and blue filters. The data was recombined on Earth to create a composite color image. The result was startling. The black and white images from 975 had shown a stark rocky world. The color images revealed a landscape bathed in a suffocating deep orange glow. There were no other colors. The rocks were orange. The sky was orange. The horizon was orange. This was not a malfunction. It was a result of atmospheric physics. The atmosphere of Venus is so thick that it acts as a massive filter. It absorbs the blue and green wavelengths of sunlight as they pass through the clouds. Only the red and orange wavelengths reach the surface. To verify this, the lander carried a color calibration chart within the camera's field of view. The chart contained strips of white, red, and blue paint. In the transmitted image, the white strip appeared orange. The blue strip appeared almost black. This proved that a human standing on Venus would see the world in sepia tone. The brain not be able to color correct the scene because there is no white light reference. The color imagery from Venera 13 and 14 profoundly disturbing in ways that the black and white images had not been. The monochromatic photographs had presented Venus as a harsh but comprehensible place. The landscape of rocks and plains was alien but not incomprehensible. The addition of color changed everything. The orange glow that suffused every image created a sense of wrongness. It was not the color of any terrestrial landscape. It was not the rusty red of Mars or the gray of the moon. It was a sickly, pervasive orange that seemed to emanate from the atmosphere itself. The revelation that this was not a camera malfunction or a processing error, but rather the actual color that human eyes would see on Venus, almost more disturbing than the temperature and pressure readings. If a human were somehow able to stand on Venus, they would not see a world of familiar grays and browns. They would see only orange. Every rock would be orange. Every shadow would be orange. The entire visual world be compressed into a single suffocating color. The psychological impact of such an environment would be devastating. The implications of the color images extended beyond mere visual perception. The fact that blue and green wavelengths were being absorbed by the atmosphere revealed something profound about the chemical composition and structure of Venus's clouds. The clouds were not merely water vapor or ice crystals. They were composed of compounds that had specific absorption characteristics in the visible spectrum. Later analysis would reveal that the clouds were primarily composed of sulfuric acid droplets. Among other compounds, the sulfuric acid clouds were not just a barrier to visibility. They were actively filtering the sunlight, removing the cooler wavelengths, and allowing the hotter red and orange wavelengths to dominate the landscape. This was a form of extreme environmental selection, where the atmosphere itself determined what colors could reach the surface. Venera 13 also broke new ground in audio. It carried a Groza 2 microphone. This instrument is designed to detect seismic activity and atmospheric discharges, but it also functioned as a standard audio recorder. It captured the first sounds ever recorded on another planet. The recording revealed two distinct types of noise. The first was the wind. The telemetry indicated a wind speed of roughly half a meter per second. On Earth, this is barely a breeze. On Venus, the air is 60 times denser than Earth's atmosphere. A wind moving at half a meter per second pushes with significant force. The microphone picked up a low, constant aerodynamic drone as the thick air flowed over the lander structure. The second sound was mechanical. The probe successfully deployed a pneumatic drill to collect a soil sample. The microphone captured the sharp, explosive sound of the pyrotechnic charge firing the drill mechanism. It then the grinding noise of the bit cutting into the basaltic rock. This audio confirmed that the dense atmosphere was an excellent conductor of sound. The environment was not just hot and pressurized, it was noisy. The recording of sounds on Venus was a unique achievement in planetary exploration. For decades, the exploration of space had been almost entirely visual. Instruments and cameras collected images and spectroscopic data, but the actual soundscape of other worlds remained unknown. The voice of Venus, when finally captured, was a strain of atmospheric noise and mechanosounds. The low drone of the wind was unlike anything heard on Earth. On Earth, produces sound primarily through turbulence and the vibration of objects. On Venus, the extreme density of the atmosphere meant that slow-moving air produced significant aerodynamic effects. The drone was constant and pervasive, suggesting an environment completely alien to human sensory experience. A human standing on Venus would not hear the gentle whisper of a breeze. They would hear a constant, powerful roar, even in conditions of relatively calm air. The grinding sound of the drill into the basaltic rock provided another window into the Venusian surface. The rock was hard and dense, requiring significant force to penetrate. The drill was designed to operate in the harsh environment, and the recording confirmed that it functioned as intended. The combination of sounds created a picture of an active, dynamic environment. Venus was not silent. It was a world of constant sound, where the wind roared and machinery screamed as it penetrated the hostile landscape. For anyone listening to the recording back on Earth in 1982, it must have been a visceral and disturbing reminder of how utterly alien the surface of Venus was. The sounds were recognizable enough to be somewhat familiar, but wrong enough to be deeply unsettling. Venera 14 landed 4 days after its twin on March 5, 1982. It touched down in a land region roughly 1,000 kilometers away from the Venera site. The terrain here was flatter and smoother. It resembled a cracked pavement of basaltic rock. The mission objectives were identical to the previous landing. The probe needed to photograph the surface, analyze the atmosphere, and physically test the ground. One of the key instruments on the lander was a spring-loaded arm. This device was designed to swing out from the base of the probe and strike the ground with a known force. By measuring how far the arm penetrated the soil, scientists could determine the physical density and pressability of the Venusian surface. It was a simple mechanical test intended to tell us if the ground was soft dust or hard rock. The landing sequence was automated. First, the probe secured its footing. Second, the cameras began their operation. The lenses were covered by titanium caps during the descent to protect the optics from the heat and pressure. Once on the surface, pyrotechnic charges fired to eject these caps. The caps popped off, clearing the view for the telephotometers. On Venera 14, the lens cap ejected exactly as planned. However, it did not roll away. It landed directly on the spot where the compressibility arm was programmed to strike. A few moments later, the arm deployed. It swung down and hammered the object directly beneath it. The telemetry sent back to Earth indicated that the surface of Venus was incredibly hard and rigid. It showed zero compressibility. This was technically accurate data. The probe was not measuring the soil. It was measuring the titanium lens cap it had brought from Earth. The camera scanned the area and sent back an image confirming the failure. The photograph clearly shows the arm pressing firmly down on the center of the discarded lens cap. The actual surface of Venus lay only centimeters away untouched. The incident remains the most famous mechanical failure in the history of the program. It highlighted the immense difficulty of remote operations. The engineers had successfully navigated millions of kilometers of space, survived re-entry, and landed in hell, only to be defeated by a piece of their own safety equipment. The failure of the Venera 14 compressibility test was simultaneously tragic and almost comedic. After overcoming so many enormous obstacles, the mission was undone by a simple mechanical mishap. The engineers had anticipated so many potential problems. They had designed the spacecraft to withstand impossible conditions. They had created innovative solutions to unprecedented engineering challenges. Yet they had not accounted for the possibility that the lens cap would be ejected directly into the path of the measurement arm. It was a failure of contingency planning, a blind spot in an otherwise comprehensive design. However, the incident also revealed the importance about the nature of remote space exploration. No matter how carefully a mission is planned, no matter how many contingencies are anticipated, the actual environment of another world will always contain surprises. The unexpected interaction between the lens cap and the compressibility arm demonstrated that space exploration is as much art as it is science. The engineers were operating in an environment they had never experienced directly, making decisions based on theoretical models and the limited data from previous missions. Despite the failure of one instrument, Venera 14 did successfully collect color images and atmospheric data. The images showed a landscape similar to that encountered by Venera 13, with the same pervasive orange coloration. The atmospheric data confirmed the readings from the earlier mission. The soil analysis equipment, while unable to measure compressibility due to the lens cap incident, was able to collect samples and conduct chemical analysis. The mission represented us even in the face of the mechanical failure. The sheer amount of data collected by the Venera 13 and 14 missions represented a dramatic leap forward in human understanding of Venus. The planet was no longer a mist world hidden beneath impenetrable clouds. It was now a known place, a world of orange rocks and crushing pressure, of extreme temperatures and hostile atmospheres, but a known place nonetheless. The mission data sat in the archives for 30 years. The scientific consensus remained that Venus was sterile. The surface temperature and pressure made organic chemistry impossible. In 2000, however, Leonid Kamenin published that challenged this view. Kamenin was not a fringe theorist. He was a respected contributor to the original Soviet space program. He decided to re-examine the raw, panoramic sequences from Venera 13 using modern digital image processing techniques. His analysis focused on the timeline of the images. The telephotometers did not take a single snapshot. They scanned the scene repeatedly over the course of the probe's life. By aligning these sequential scans, he looked for changes between the frames. He found them. He identified several objects that appeared to behave erratically. The most prominent anomaly he named the scorpion. In the early scans, the soil is empty. In a scan taken 7 ending, a structured object appears. It is approximately 15 centimeters long. It seems to have a central body and a curved tail. In the subsequent scans, the object is gone. Kamenin argued that the object emerged from the soil, remained visible for a short period, and then moved out of the frame. He also identified an object he called the black flap. This object appeared to change shape and position relative to the probe. He famously stated that these objects emerged, fluctuated, and disappeared. He suggested that the inhabitants of Venus might utilize a form of life based on exotic chemistry rather than carbon and water. The claims made by Kamenin were extraordinary and generated considerable interest among both scientific and popular audiences. The possibility of life on Venus had long been dismissed as impossible. The surface conditions seemed absolutely incompatible with any known form of life. However, Kamenin's analysis suggested that perhaps life could exist in forms radically different from what we know on Earth. Perhaps there were organisms that thrived in sulfuric acid clouds and survived crushing pressure. Perhaps the Venera 13 lander had not just observed Venus, it had observed Venusian life. The idea captured the public imagination. Here was a respected scientist, someone who had been part of the original Venus missions, suggesting that we had been looking at evidence of alien life for decades without recognizing it. The images taken in 1982 might contain photographic evidence of creatures from another world. The global scientific community rejected his conclusions. NASA scientists and other Russian experts provided a mechanical explanation for the anomalies. They argued that the scorpion and the flap were likely pieces of the lander itself. The probe was wrapped in layers of insulation and plastic. As the internal temperature rose, these materials began to melt, peel, and fall off. The movement was biological. It was the result of the lander disintegrating under the thermal stress. The shifting shadows were likely caused by the angle of the sun on the settling of the lander into the soft soil. Subsequent analyses and improved image restorations have confirmed these features as artifacts, noise, or detached components of the lander rather than evidence of life. Despite the rejection of the biological theory, the analysis revealed something unsettling about the footage. The surface of Venus was not a static painting. It was a dynamic place. Things moved, shifted. The lander groaned and warped. The footage did not show a dead world. It showed a violent interaction between the machine and the environment. The impossible shapes were likely the dying convulsions of the probe itself, captured in slow motion by the scanning camera. The re-examination of the Venera 13 images by Kamenin and the subsequent rebuttal by the scientific community illustrated the challenges of interpreting data from remote space missions. The images were not high-resolution photographs. They were line-by-line reconstructions from telemetry data, each pixel potentially subject to noise, distortion, and processing artifacts. When examining these images after they were taken, researchers had to distinguish between genuine phenomena and imaging artifacts. This was far from straightforward. The human brain is remarkably good at seeing patterns, even where none exist. We see faces in clouds and movement in static images. When examining the grainy, low-resolution reconstructions from Venera 13. It was almost inevitable that ambiguous shapes would be interpreted as evidencing more interesting than mere instrumental noise. The scientific consensus that the anomalies were artifacts of the lander disintegrating was almost certainly correct. It was based on reasonable inference rather than absolute proof. We did not have definitive evidence of what the scorpion and the black flap were. We only had good explanations for what they probably were not. The camera on Venera 14 was the last eye humanity opened on the surface of Venus. After 1982, the Soviet priorities shifted. The engineers realized that landing in random spots provided excellent close-up data, but it could not map the entire planet. To understand the geology of Venus on a global scale, they needed to see through the clouds from orbit. Venera 15 Venus launched in 1983. They did not carry landers. They carried massive synthetic aperture radar systems. These probes mapped the northern hemisphere of the planet. They revealed shield volcanoes, lava channels, and tectonic fractures. The data was scientifically invaluable, but it was abstract. It was a topographic map, not a photograph. The final Soviet missions to Venus, Vega 1 and Vega 2, launched in 1985. These were HIBE missions designed to intercept a comet. They dropped off landing units at Venus on their way to the comet. The Anders focused on soil chemistry and atmospheric analysis. They also deployed balloons that floated in the upper atmosphere to measure wind speeds. They did not carry cameras. The engineers decided that the weight of the imaging system was better spent on other instruments. With the collapse of the Soviet Union, the program ended. The shift from surface landers to orbital radar mapping represented an evolution in mission strategy. The Soviet space program had proven that surface could function on Venus, at least for limited periods. Now the challenge was to expand the understanding of the planet as a whole. Radar could penetrate the thick clouds that were opaque to optical telescopes. It could map the entire surface, revealing the global scale of Venus's geological features. The radar data showed that Venus was a world of volcanic activity. Vast shield volcanoes dominated many regions. Lava flows covered enormous areas. Tectonic features suggested that Venus's crust was still geologically active. However, rare data, while scientifically rich, lacked the immediacy and visceral impact of optical photographs. A radar map was an abstract representation of terrain. An optical photograph, what the surface actually looked like. The choice to abandon optical imaging on the final missions was driven practical considerations and mission objectives. But it meant that the body of knowledge about Venus's visual appearance remained fixed at the 1982 missions. The data from the Venera missions was stored on magnetic tapes. Over time, the physical media began to degrade. The images that appeared in newspapers and scientific journals in the 1970s and 1980s were often grainy and low contrast. They were analog reconstructions of digital signals. In the 2000s, a new generation of researchers began a process of digital archaeology. They went back to the raw telemetry data. Modern computers could process the signal noise much more effectively than the mainframes of the 1980s. They filled in missing pixels and corrected the geometric distortion caused by the panoramic mirrors. This restoration work revealed details that had been invisible for decades. The new images showed the texture of the soil and the layering of the bedrock with unprecedented clarity. They revealed that the horizon line was further away than previously thought. The resolution of the restored images approached what the original teletometer systems had actually captured before transmission noise and reconstruction errors had degraded the data. The process of digital restoration of the Venera image represented a fascinating intersection of space exploration, survival science, and modern computing. The telemetry data from missions conducted in the 1970s and early 1980s was ultimately just strings of numbers. These numbers had been converted into images through processing algorithms that were, by modern standards, crude and limited by the computing power available at the time. The original missions had used mainframe computers to reconstruct the images. These computers had been immensely powerful for their era, but they were limited in their ability to correct for noise and artifacts in the telemetry signal. When the raw telemetry data was reprocessed using modern algorithms and modern computers, many of the degradations in the original images could be corrected. Missing pixels could be inferred from neighboring data. Geometric distortions caused by the scanning mirror system could be mathematically reversed. The result was images that were closer to what the telephotometer systems had actually seen. It was as though the Venera missions were being reflown a second time, using technology that had been unavailable to the original engineers. Today, these restored images remain the only direct ground-level optical photographs ever taken of the Venusian surface. Subsequent orbital radar missions and more recent observations, including near-infrared detections by the Parker Solar Probe that sensed faint thermal emission from the surface through atmospheric windows, have added valuable new perspectives. However, no mission since returned new photographs captured from the surface itself. Every other image of Venus you see is either a radar map, an artistic rendering, or a photo of the cloud tops. The color images from Venera 13 and 14 remain the most and immediate window we have to what the surface of Venus actually looks like. In an era of high-resolution satellite imagery and space probes that stream high-definition video, the fact that our most recent close-up images of another planetary surface come from the early 1980s is a humbling reminder of the extreme difficulty of space exploration. We have sent rovers to Mars that stream high-definition video daily. We have flown past Pluto and seen its icy surface in exquisite detail. Yet for the planet closest to Earth, our visual understanding is frozen in 1982. We rely on data collected by a titanium sphere melted 40 years ago. The reasons why no subsequent landers have reached Venus's surface are complex and multifaceted. After the Soviet program ended, Venus exploration fell out of favor. The planet was considered too hostile, and the scientific returns too limited to justify the enormous expense and technical challenge of landing another probe. The United States space program had never seriously invested in Venus landers, focusing instead on Mars rovers and orbital missions to other bodies. The European Space Agency and other space agencies conducted orbital and atmospheric missions to Venus, but none mounted a surface lander program. In a sense, Venus had been conquered and then abandoned. The dramatic achievements of the Venera missions had proven that human engineering could overcome almost any obstacle, but they had also demonstrated how expensive and difficult it was to do so. When the Cold War ended and the space race wound down, the urgency that had driven the Soviet program dissipated. Budget priorities shifted. Attention turned to other destinations. The technical challenges of building a new Venus lander remain enormous. The engineering difficulties that the Soviet program had overcome in the 1970s and 1980s are no less formidable today. In many respects, the problem has become more difficult. Modern spacecraft rely on silicon-based electronics that are even more sensitive to heat than the systems of the 1970s. Modern power systems have different requirements than the batteries that powered Venera probes. The lessons learned by the Soviet engineers would need to be learned and adapted to contemporary engineering standards. It is possible that a new Venus lander could be built. The cost would be enormous, and the political will to fund such a project remains limited. Mars, with its more moderate conditions and its potential for the discovery of past or present life, has captured the imagination and the budget allocations of space agencies worldwide. Venus, for all its scientific interest, remains the road not taken by contemporary space exploration. The legacy of the Venera program extends far beyond the specific data collected by the missions. The program demonstrated that a nation with sufficient political will and engineering talent could overcome almost any technical obstacle. The Soviet engineers had faced a problem that seemed nearly impossible. The conditions on Venus were so extreme that many scientists had argued that no spacecraft could survive. The response was not to abandon the effort, but to fundamentally rethink spacecraft design. The engineers created solutions that were elegant in their simplicity and profound in their effectiveness. The titanium sphere, the phage materials, the mechanical telephotometer, the innovative cooling systems, these were not just engineering solutions. They were statements about human ingenuity and determination. They were proof that the limits, what was possible, could be pushed further than anyone had thought. The Venera program also provided a crucial foundation for our understanding of planetary atmospheres and surface conditions. The atmospheric measurements from the Venera missions, data that was essential for understanding the runaway greenhouse effect on Venus. The chemical analysis of the atmosphere showed that the clouds contained sulfuric acid. The measurement of surface temperature and pressure established the extreme conditions that made Venus the hottest planetary surface in the solar system. The geological data from the surface missions showed that Venus was a volcanically active world. All of this information was gathered that are dated to the edge of technical feasibility. Each data point was hard-won, purchased with enormous effort and engineering ingenuity. The information was valuable precisely because it had been so difficult to obtain. The photographs from Venera 13 and 14 occupy a unique place in the history of space exploration. They are not the most beautiful images ever taken of another world. The Mars rover images are more detailed and in many ways more striking. The images of Jupiter and Saturn from the space probes are more visually dramatic. The Hubble Space Telescope images of distant galaxies are more profound in their implications. Yet the Venera images have a particular power. They show not just a world, but a victory against impossible odds. They are images that should not exist. They document a place that conventional wisdom said no machine could photograph. The orange rocks and the orange sky captured in those images represent the triumph of engineering over environmental hostility. They are pictures of hell, taken by machines that descended into the inferno and returned to tell the tale. The color of the Venusian landscape, as captured by Venera 13 and 14, has become iconic. The orange glow has become the visual symbol of Venus in popular culture and scientific communication. When artists depict Venus, or when documentaries show reconstructions of the planet's surface, they use the orange coloration by the Venera images. This coloration is scientifically accurate. It represents the actual filtering effect of the Venusian atmosphere on sunlight, yet it also has a psychological impact that goes beyond mere color accuracy. Orange is the color of warning in many human cultures. Orange suggests heat and danger. The orange landscape of Venus is not just scientifically accurate, it is emotionally appropriate. It visually communicates the inhospitable nature of the environment. Until a new lander survives the descent, the yellow and rocky plains of the Venera panoramas remain our only true view of hell. The future exploration of Venus remains an open question. The planet is scientifically fascinating. It is a laboratory for understanding planetary atmospheres, greenhouse effects, and the potential habitability of exoplanets. It is possible that the Venus harbors life in its upper atmosphere, where temperatures are more moderate. The clouds of Venus are not as hostile as the surface, and some scientists have speculated that microbial life could exist at those altitudes. The exploration of Venus's atmosphere is a more feasible goal than surface exploration, and several proposed missions aim to send balloons or other platforms into Venus's clouds. However, the surface remains the great unexplored frontier of Venus. The surface holds information about the planet's geological history, its internal structure, and the processes that drove it to its current hellish state. That information remains locked away behind the crushing pressure and searing heat, waiting for the next generation of spacecraft and the next generation of engineers willing to tackle the challenge. The Venera program represents a crucial chapter in the history of space exploration, yet it remains remarkably little known in popular culture compared to the American space program. The Saturn V rockets and the Apollo missions dominate popular imagination. The Mars rovers are household names. The Voyager probes are celebrated as achievements of human exploration. Yet the Venera missions, which were in many respects more technically difficult and which achieved equally remarkable results, remains well known outside of scientific circles. This is partly a consequence of the geopolitical context in which the missions occurred. Venera program during the Cold War, and there was less enthusiasm in the West for celebrating Soviet achievements. Partly it is as a function of the nature of the missions themselves. The images and data from Venera missions were not as visually dramatic or as easy to communicate to general audiences as the Apollo lunar samples or the Mars photographs. The orange runs do not capture the imagination in the same way that the footprints on the moon do. Yet the Venera program deserves to be remembered, one of the great achievements of human space exploration. The missions took place during an era of rapid technological progress, but they still required innovations and engineering solutions that were remarkable for their time and that remain impressive today. The engineers who designed these spacecraft worked with computers that had less processing power than a modern smartphone. They built spacecraft that had to function in an environment more hostile than anything experienced on Earth. They created imaging systems that transmitted data across millions of kilometers of space through radio waves, and then reconstructed detailed panoramic images from that telemetry. The achievements are remarkable, and the legacy of the Venera program extends far beyond the specific data collected. The photographs from the Venera missions are windows into another world. They are evidence that human ingenuity can overcome seemingly insurmountable obstacles. They are reminders that there are places on other worlds where human machines can go and capture direct evidence of what exists there. In an era when we are beginning to think about long-term space exploration and human missions to other worlds, the Venera missions offer both inspiration and caution. They show what is possible with sufficient determination and resources. They also show the enormous costs and difficulties involved in reaching even the closest planets. The future exploration of Venus remains uncertain. Budget priorities shift. Political circumstances change. Scientific interests evolve. Yet the orange rocks captured in the Venera images remain as a testament to an earlier era of space exploration. When the Soviet space program achieved remarkable feats with limited resources, and when the exploration of Venus seemed like an achievable goal, until new landers reach the surface and capture new images, the photographs from 182 remain the most direct evidence we have of what the surface of the planet closest to Earth actually looks like. The Venera legacy endures.